All right, today we are decoding the secret that's hidden inside this really complex-looking engineering problem. And you know what? Believe it or not, the answer explains how your thermos works and even why your house stays warm. Let's get right into it. So, this looks pretty intimidating, right? It's actually from the entrance exam for the Indian Institute of Technology, which is one of the toughest in the entire world. But if you boil it all down, past the numbers and the jargon, it's really just asking one simple thing. How do you stop something from losing heat? And that secret? It's the exact same principle that's at work inside a thermos, a cooler, or even just the walls of your home. It's all about controlling heat. Okay, so let's start by looking at this problem, but not as a test. Let's treat it more like a set of clues. We're just gonna deconstruct it, piece by piece. And I promise, by the end, you'll see the core idea isn't so complicated after all. We just need to find the right key to unlock it. And that key, it actually has a name. Thermal resistance. This is the big idea, the central concept we need to get our heads around to solve this whole puzzle. Okay, so the textbook definition is that thermal resistance is a measure of how well a material can stop or slow down the movement of heat. But what does that actually mean? Here's a great way to think about it. Imagine heat is a runner, and it's trying to get from a hot area to a cold one. Well, thermal resistance is basically the obstacle course that we put in its path. The harder the course, the slower the runner. Simple as that. So it's really straightforward. Materials with a high thermal resistance are amazing at blocking heat. We call them insulators. Your thermos, for instance, is engineered to have the highest thermal resistance it possibly can. Okay, now that we've got that concept in our back pocket, let's go back to our cylinder and start looking for the clues that tell us about its obstacle course. The first set of clues we need to check out are the physical dimensions of the cylinder itself. The problem gives us two key measurements. First, an outer diameter of 5 centimeters, and then an inner diameter of 3 centimeters. See that space between those two numbers? That 1 centimeter of thickness? That's the actual track of our obstacle course. It's the wall of glass that the heat has to fight its way through to escape. So a thicker wall means a longer and tougher course. But the length of the course is only half the story. The type of obstacles you put on that course matters just as much, and that brings us to our second clue, the material. This is where a related idea comes into play, thermal conductivity, which we usually represent with the letter K. Now, if resistance is how much a material blocks heat, conductivity is basically the opposite. It's how much it helps heat flow. The problem tells us the thermal conductivity of this glass is 1.05, but what does that even mean? Is that a lot? Is it a little? It's kind of hard to tell without some context. Well, this makes it super clear. A material with high conductivity, like a metal spoon you leave in hot soup, acts like a heat superhighway. It just lets the heat zip right through. But a material with low conductivity, like our glass, is that heat obstacle course, slowing the whole journey way, way down. So we've pretty much decoded the puzzle. But why is this idea of resisting heat so important when you're not, taking a crazy hard exam? Because once you really understand how to control the flow of heat, you realize you can build a more comfortable, a more efficient, and even a safer world. It's everywhere. I mean, seriously, think about it. This one principle is everywhere. It's the vacuum gap in your thermos. It's the fiberglass insulation in your walls, literally lowering your energy bills. It's used to safely contain super hot fluids in factories. It's how we keep our phones and computers from overheating, and it's even in the puffy layers of your winter jacket. So you see, that complex exam question wasn't really about a glass cylinder at all. It was asking a much bigger question. How do we use the right material with the right thickness to build the absolute perfect obstacle course for heat? It's about engineering control over this totally invisible force. So we've pulled back the curtain on the science of controlling heat. It kind of makes you wonder, what other invisible forces are being engineered all around us, just hiding in plain sight?